All right, so a few announcements just to start off, and then a recap just so we know where we're at, and then a bit of a plan for finishing off the semester, and then we'll just continue to work through the material after that. So first, last Monday, we wrote the third quiz. I'm almost done marking the third quiz. I just have to finish one question. So I should have those back to you by the end of the day for sure. And I'm hoping actually before the morning is over. So you can expect those results by the end of today. On Friday, the fourth assignment is due. The the fourth assignment covers essentially post stratification, or rather stratification with ratio estimation. It covers cluster sampling. It covers two-stage cluster sampling. So that's all material that we completed last week, I believe, because we're into a new lecture set at this point. So these are things that we've been able to finish for quite some time. And then hopefully those assignment marks will get turned around fairly quickly. The TA is pretty good, so I expect that you'll have all your results back before the final exam, which is on April 16th. So that's a week from Friday. What we're going to do is we're going to continue to work through new material today. So we'll finish lecture set 6. We don't have very much left in lecture set 6. And then we'll start lecture set number 7. Lecture set number 7 is essentially a lecture set that covers additional topics in survey sampling. So it's sort of an amalgamation of different strategies you can use to, for example, estimate population size and deal with non-response. So effectively what it is strategies for handling some of the errors that we can expect in survey sampling. So we'll start that today, and we'll continue to work through that on Friday. And then wherever we get to by the end of class Friday, so if that's completion of lecture set 7, then that's great. And if not, we'll just stop there. Since, again, the final exam is a week from Friday, it seems fair to finish with any new material a week in advance so that everyone has time to at least look it over and familiarize themselves with some of the new concepts. And then on Monday's class, we will have effectively a review session where we will go over and discuss what we have seen in the class, what you can expect on the final, that sort of just a standard review essentially. Practice problems, practice problems, formula sheet, all those sort of things will be posted promptly so that you have them in time to prepare. The final exam is a cumulative exam. So yeah, it will cover everything from the start of the course. Lost my train of thought there. Formula sheets, cumulative, review session. So for the final exam, it will operate the same way that the quiz is operated. Obviously today we're having lecture online. I just thought with, the announcement that came out yesterday that maybe it would just be better to do today online, but, hopefully by next Friday, things have settled down a little bit. But regardless, the university remains open, so we can still use the classroom for the final. So we'll have the same options that we had for the quiz. If you would like to come in and write in the classroom, then you're more than welcome to do so, and I will be there. And if you would prefer to write online, then of course you're welcome to do that as well. You just please let me know if you would like to write online, and I will arrange for the exam to be sent to you via CrowdMark. As per with every quiz, just send me an email and let me know. I will assume you're coming in unless I hear from you. I'm sure it'll be like the same group of people that would prefer to write online, but it's just better to have a record of those requesting it. So yeah, please let me know at your earliest convenience if you would prefer to write from home. I'll send out an email reminder and all that sort of thing leading up to the exam. And again, it'll operate the same way as the quizzes. It's just kind of a really long quiz because we have 3 hours to write in, whereas the quizzes were only an hour. Okay, does anyone have any questions? So again, quiz 3, I'll have it back to you by the end of today. Assignment 4 is due on Friday. Hopefully that'll get turned around pretty quick. And then the final exam is a week from Friday, so April 16th from 9 to 12. Okay, and then that'll be in the lecture room or online. Any questions? Okay, I'm not seeing any. All right, so let's just do a little bit of a review so we know where we're picking up. We're still working through lecture set number 6. Lecture set number 6 was devoted to studying sampling protocols that had an uneven probability of selection. So we talked about 2 general sampling strategies, which were sampling with replacement and sampling without replacement. In each case, we have discussed estimation of the mean and we have discussed estimation of the total. When sampling with replacement, we noted that our computation of the mean and the total was actually quite straightforward because every single unit has a consistent probability of appearing in the sample. Whereas when we sampled without replacement, we had to effectively change our selection probabilities for each of the units that were being pulled because the probability of observing that unit changes when one of the other units is pulled into the sample. Again, in both cases, we showed how to estimate the mean, how to estimate the total, and we effectively used empirical proof to show that these estimators were unbiased for the quantity of interest. What we had left off talking about was cluster sampling with unequal weights. Okay? And in this situation, so when we want a cluster sample but not have an equal weight assigned to each of the clusters, one of the potential strategies that we can use is sampling with probabilities proportional to the size. So what we're saying here is that the selection probabilities for each of the clusters can be directly proportional to the actual size of that cluster. So you can imagine if you have a population with, say, 1,000 units in it, and you have 5 different clusters, but the clusters are not equally sized. So maybe the first cluster has 300 units, and then the second cluster has 100 units. Then you have 2 clusters with 150, and then you have the last cluster with the remaining number of observations. Our selection probabilities will be based off of the sizes of those clusters. Okay. Now, what's interesting about this approach is when you use a selection probability that is proportional to the size of the cluster. So you can see in equation 2, we have delta I is equal to little mi divided by capital M. Right? So little mi is the number of elements within, well, each of the clusters or within the sample. And then capital M is the number of elements within the population. So we can see that equation 2 is actually just giving us the ratio of the cluster size to the population size. When we use this selection probability and we include it in the estimator for the total that we derived when studying sampling without replacement, you can see that our estimator becomes tau hat is equal to capital M over little n multiplied by the sum of the estimated means from each cluster. So this looks pretty similar to the general estimator for the mean that we would expect to see across any of our sampling schemes. This is basically just a weighted average multiplied by the number of elements within the population. And from this, we can show that the estimate of the mean is simply the average of the means from each of the cluster. So when we use a cluster sampling scheme, but our estimators are based off of selection probabilities that are proportional to the size of the clusters, we actually get a very fundamental form for our estimator of the population mean and our estimator of the population total. Right, so we can summarize those estimates on slide, or I have those estimates summarized on slide 14. Again, these behave pretty much as you would expect them to behave. You can see that in the case of the mean estimator, the variance looks, again, more or less like what you would expect it to look like. We have the variation around the overall mean of each of the cluster means divided by n minus 1, and then we have the 1 minus n out front from the estimator. And then for the total, we basically have the exact same thing, just multiplied by m and multiplied by m squared. So these forms follow essentially what we have seen throughout each of the different sampling strategies that we've talked about in the course. So to illustrate this, we're going to just walk through a very basic example. Okay, so in this example, we have an auditor wishes to estimate the average number of sick leave days among a large firm with 8 divisions. So in our table, we have division 1 through 8. We have the number of employees in each division. And then we have a cumulative range representing essentially like an employee ID number. So if you start from division 1, employee 1 in division 1 is number 1 up to 1200, which would be employee 1200 in division 1. And then in division 2, you start at 1201, and that goes to 1650 because there's only 450 people in division 2. Then you go to division 3, and it's the same logic. So you start at 651, and then you increase by 2100 people because there's 2100 people in division 3, etc. So each of the divisions here are the clusters. Okay, so we have a total of 8 clusters, right? The number of employees, well, this is going to be the size of each cluster. Which would be capital MI. Okay. And then the cumulative range, which is shown here, this is just like an ID number. So this would be like employee ID. Okay, so we want to estimate the average number of sick leave days used per person, and then we want to bound that error. So pretty traditional style of problem, basically just a confidence interval setup. Should probably start with part A instead of part B though. Okay, so to do this, we're going to devise a little scheme, talk about how we could select the clusters, and then go forward from there and show the estimation procedure. Okay, so we'll call this sampling protocol. Okay. All right, so step 1, we will randomly select 3 people using IDs between 1 to 12,950. Sorry, so I said step 1, randomly select 3 people using the IDs between 1 and 1,000, 1,200, 950. Okay. Okay, so this is going to give us a sample. Okay, so suppose observations 0, 2, 0, 1, 1, 0, 7, 9, 7, 2, and 1, 0, 2, 8, 1 are selected. So this gives us to divisions 3, 6, and 8. All right. Okay, so then once we have the divisions, we would basically just be computing the average number of sick days per division. Okay, so suppose the average number of sick days per division are mu hat 1 is equal to 4,320. This would actually be, sorry. So this corresponds to division 3, 5, and 6. So that gives little n equals 3. Okay, and then we'll let mu hat 1, mu hat 2, mu hat 3 be averages of divisions 3, 6, and 8. Okay, so we randomly selected 3 people. From those 3 persons, or from those 3 ID numbers, we got our 3 divisions. And then I'm just declaring that mu 1, 2, and 3 will be the averages of those 3 divisions respectively. Okay, so now let's suppose that the average number of sick days per division can be, or our mu 1 is equal to 4,320 divided by 2,100. That's the sample size. So we have total number of sick days divided by sample size for division 1. So that gives us 2.06. For division 6, our total number of sick days is 4,160 divided by the division size, which is 1,910. So that gives us 2.18. And then for the third division, for this 8th division, the total number of sick days is 5,790, which is divided by the division size, which is 3,200. And that gives us 1.81. Right. Okay. So then we would have mu hat PPS is equal to 1 over little n multiplied by the sum from I equals 1 to n of each mu hat I. Okay, so we can see pretty clearly that this is just the average of the 3 means, which is equal to 2.02. Okay. And then if we wanted to bound this, we would have the variance of mu tilde PPS is equal to 1 over n times n minus 1 multiplied by the sum from I equals 1 to n of mu hat I minus mu hat PPS. Okay, so 1 over 3 times 3 minus 1 multiplied by, and then we'll have 2.06 minus 2.02 squared plus 2.18 minus 2.02 squared plus 1.81 minus 2.02 squared. And that gives us, of course, 0.0. Okay, so then the bound is going to be 1.96 multiplied by the square root of 0.0150. Sorry, one sec. Equals. Oh. There we go. And then our bound is square root variance mu tilde PPS 1.96 0.01183 repeating equals 0.214. All right. Any questions? Okay, so that brings us to the end of lecture set number 6. So again, lecture set number 6 discussed essentially sampling strategies where the probability of selection was unequal. So in this situation, or in this lecture set, we talked about sampling with replacement and sampling without replacement in the general scheme. And then we talked about an application within cluster sampling where we sampled with unequal sizes. But the probabilities of selection were proportional to the cluster size. And in the end, the result that we get from that strategy is actually a very, sort of refined estimate for the mean and for the variance of said mean. And the examples of those are what we just worked through. All right. So now what we're going to do is start lecture set number 7. And lecture set number 7, as you can see, it's just titled Additional Topics in Survey Sampling. So there's a number of different concepts that we're going to work through in this lecture set. They're all sort of separate ideas. So direct sampling and inverse sampling are related because the goal is the same. Density and size estimation via quadrants is a slightly different idea just based off of data that we could be working with. Then we have ideas of adaptive sampling and interpenetrating sampling or subsampling. This is related to non-response error. Okay, so we're kind of just going to bounce around a bit and try to address some of the different problems that we've talked about throughout the course. So as you might recall, we have seen 5 different survey sampling schemes. So we talked about simple random sampling, stratified sampling, systematic sampling. We talked about that before, stratified, but cluster sampling and 2-stage cluster sampling. Across all of those different sampling strategies, there are a number of different, there are a number of issues that can occur when you're collecting information, for example, or even when you're going to make your estimations or to perform estimation. So for example, when we want to estimate a population total, or even when we want to estimate the bound attached to a particular estimate, we require capital N. So we require the population size. If we don't have the population size, we will typically just assume that it's very large. So we can, for example, ignore the FPC. But if we're in a situation where we wanted to, say, estimate a population total and we don't know the population size, this creates an issue for us because we need population size to estimate said total. We know that in the cluster sampling scheme, we have ways around this because we can, for example, use the sizes of the sample clusters to estimate the sizes of of all of the clusters in the population. And sorry, what I mean is we can use the sizes of the sampled clusters to find the average size of each cluster and use that as an estimate for the average size of all of the clusters in the population. But if we don't have the total number of observations, we have to use an entirely different strategy to estimate the total. In other situations, like even in the most basic situation where we're using simple random sampling, if we don't have capital N, we can't estimate the total. So to address this, we can use effectively like a survey sampling type scheme to estimate the total of the population. So the goal in the first strategies that we're going to look at are estimating population size rather than estimating a population average, total, or proportion. So direct sampling is an approach that we can use to estimate the size of a population. Direct sampling is typically utilized when you want to estimate the size of what we can refer to as a mobile population, which just means a population that's consistently on the move across some region. So you can consider, for example, like a wildlife population of, I don't know, like bison or something like this. Okay. All right, so direct sampling proceeds in two steps. A random sample of size T is drawn from the population of interest. And then at a later date, a second sample of size little n is drawn from the population of interest. Using this information, we can estimate capital N in the following way. So we can write that n tilde, our estimator for capital N, is equal to little t divided by p hat, where p hat is little s over n. Okay? And this gives us little nt over s. So in this situation, n is the size of the second sample that was drawn. T is the size of the first sample that was drawn. And little s is the number of tagged animals in the second sample. So what I mean there is, on the first step, suppose you draw the T animals from this population, or the T observations from the population of interest. You tag those T observations and you tag those T observations and they're put back into the population. When you draw the second sample, you count the number of tags that you have recovered from the first sample. So little s is the count of the number of tagged animals in the second sample that were tagged in the original sample. Okay. The variance of our estimator for the population size from direct sampling is given in equation 1. So we have t squared multiplied by n times n minus s over s cubed. So you can see that the idea here is computationally pretty straightforward, and we're able to perform the same type of estimation style approach that we did or that we have throughout the course. So we can find an estimate and we can bound the estimate, and then we can say with some percentage of confidence what our population quantity of interest could be between. Okay, For fairly large samples, the expected value of n tilde is equal to n plus capital N times n minus t over little nt. Okay, so this will be approximately unbiased when t and n are large. And you can see, well, t or n are large. And you can see little n. Why that is true from equation 2, because we have little nt in the denominator. So in order for this second term to go to 0, we require those values to be large. Okay, so to illustrate this approach, we have the following example. A club is concerned about the number of trout in a local stream. A sampling scheme is utilized where a random sample of 100 trout are caught, tagged, and released back into the stream. Then several weeks later, a second sample of 120 trout were caught. Suppose that in the second sample, only 27 tags were counted. Estimate capital N and place a bound on the error. Right? So this is all pretty straightforward. We just have to declare the different components of our sampling scheme or sampling protocol, and then we can use these to estimate and bound it. Okay, so in part A, we have little n is equal to, or sorry, we have little s is equal to t is equal to 100, so that's the first number caught. Then we have little s is equal to 27, the number of tagged elements that were recovered. Sorry, and then we have little n, which is 120. Right. So again, we have first sample, then we have second sample, and then we have tags. Okay, so n hat is equal to little n times t over s. Right, so this is going to be 120 multiplied by 100 divided by 27. And that gives us 444.4 repeating. Okay, so our estimate of the population size, so our estimate of the total number of trout in this local stream is around 445. Okay, so we can bound this in the usual way. Okay, so we're going to have the variance of n tilde is equal to t squared multiplied by n minus s divided by s cubed equals 100 squared multiplied by 120 minus 27 divided by 27 cubed, which is equal to 5,669.867. So then the bound will be in the usual way 1.96 multiplied by the square root of our estimate of the variance, which is 150.597. So in this case, we're essentially saying that there's somewhere between 295 and 595 trout in this local stream. It's a pretty big range. Any questions? I'm not seeing any. All right, the next sampling or the next strategy for estimating the population size is called inverse sampling. So the goal of inverse sampling is the same as direct sampling. So they are both methods for estimating capital N, the size of some population. The difference between inverse sampling and direct sampling, as you can see from the slide, is that with inverse sampling, the second sample is not a fixed quantity. So what does this mean? In direct sampling, the random value is little s. So we had T, which was the number of animals caught and tagged on step 1. Then we selected a fixed size of little n on step 2. And little s was random in the sense that we didn't know how many tagged animals we would recover. With inverse sampling, step 1 is the same. So we collect a sample of size T, where T represents the number of observed and tagged observations. And then at a later date, we select a second sample of size little n, but we continue to draw until we have recovered S units. So the difference here is on step 2, little n would be random because we don't know how many observations we would have to draw until all S of our tagged units have been recovered. Okay, so when we use inverse sampling, you can see that the estimator for the population total, the estimator for the population size is the same as it was in direct sampling. So little n T over S, where each of those terms have the same definitions that they did in direct sampling. But the variance of our estimator is now given by T squared multiplied by N multiplied by N minus S divided by S squared over S plus 1. Right. Now, one of the nice things about the inverse sampling approach is that our estimator N tilde is unbiased for capital N, and our variance, or the estimator for the variance of N tilde, is also unbiased for the true variance of N tilde. All right. Okay, so to illustrate this, we have a zoologist wishes to estimate the size of a turtle population in a given geographical area. A random sample of 100 turtles are caught, tagged, and released. So that's going to be our T. And then 1 month later, a second sample of 160 turtles were caught in order for the zoologist to obtain 15 tagged turtles. So again, here we have T is equal to 100. And now we have little n is equal to 160. And we have S is equal to 15. So just like before, this is going to be the first sample. Okay. This is going to be the required number of tags. And this will be sample size or second sample needed to receive or to observe S equals 15. Okay. All right, so from this point, everything is pretty much the same as it was before. The only difference here is really just the variance, the equation for the variance of our estimator for the population size. So we have n hat is equal to nt over s. So this is going to be 160 times 100 divided by 15. And this gives us 1066.6. Okay, and then in B, we have our estimate of the variance of n tilde is going to be t squared multiplied by n multiplied by n minus s divided by s squared times s plus 1. So this will be 100 squared multiplied by 160 multiplied by 160 minus 15 divided by 15 squared, 15 plus 1, which is 64,444.4. Okay, so then our bound will be the square root of the variance of n tilde. So this will be the square root of 64,444.4, which is equal to 507.7182. Okay. Oh yeah, thanks. It's actually very nice to see that those two comments, because you don't know if like people are actually listening or not. So I very much appreciate that correction. So again, direct sampling, inverse sampling, same goal. So they're both used to estimate population size. The difference is that with direct sampling, little s is random, and with inverse sampling, little n is random. So with direct sampling, we don't know how many tagged animals we are going to recover. With inverse sampling, we have a set quota of tagged elements that we require. So the little n will change to meet that requirement for S. Okay. Yeah, maybe. I don't think they would have done it like necessarily one at a time. I mean, they probably would have started with 15 and then gone one at a time. But in this situation, the implication is that it took them 160 to catch 15. So that, I mean, would imply that maybe they had 14 and then they just kept sampling one more until they found the turtle. So yeah. You know what I mean? Cool. All right. Okay, so the next illustration, this is a different estimation procedure now. So in this example, we're talking about estimates of density and size via what are called quadrats. All right, so suppose we are sampling from a region with a total area capital A by selecting n plots with an area little a, okay? So in this case, we can write that the total area is equal to the total number of plots multiplied by the area of each plot. Okay? So this would make sense because if we think of like a square object, give me a good square, please. Or I guess a rectangular object in this case. So if this is our capital A, and we divide this into equal size plots, try and do this as best I can. I've already messed it up. Right. Well, it's not going to be quite perfect. Right. So each of these squares is a size little a. So these are all little a's in here. Right. So we're just saying that capital N would be equal to 12 in this case. So total area is equal to 12 multiplied by the area of each of the different plots. Right. Okay, so each plot, so each of the little squares marked A, so this would be like A1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. Okay, so each plot is called a quadrat. regardless of whether or not it is a square. Right? So basically, I've used a rectangle to illustrate the idea, but it doesn't necessarily have to be rectangular, but you can just imagine that you have some area, some piece of land that has a total area capital A. It's been divided into some number of separate plots. Each of those little plots is a size little a, which implies they have the same area because it's a constant across all of them. And then the total area would be the number of plots multiplied by that size, right? Okay, so little mi will donates the number of elements within each quadrat. So that's very similar to our cluster sampling scheme. So we're saying that each of these areas within the rectangle returns little mi elements. Okay. So for example, here we have M12, here we have M7, here we have M1, for example. Okay, so lambda is the density of elements per each of the different quadrats, or it's the number of elements per each of the units. Okay, so we can say that the true lambda is equal to capital N over A. So basically it's just the population size divided by the total area. So that's why we can think of it as a density, because it's essentially measuring how many elements exist per unit of area that we are utilizing within the experiment. But it's not all that different from an average size per quadrat, right? Okay, so little m bar is going to be an estimate of the number of elements per quadrat or per quadrat. And we can use little m bar to estimate the true density of the area that we are studying. So lambda hat here is going to be the estimate of lambda, which again is essentially the density. So the number of elements per unit of density that, or per unit of area that we are studying. And this is going to be little m bar over A. So A is the number of sampled, or A is the area of each of the different quadrats, and little m bar is the average of the number of elements per quadrat across the sampled quadrats. Our variance for, oh, this should be tilde here. Okay, so our variance of lambda tilde is going to be lambda hat divided by A over N, where again, N is the number of sampled plots or quadrats. Little a is the area of each of the quadrats, and lambda hat is going to be the estimate of the density of the entire region. Okay. From equation 6, we can also write estimates for the total number of elements in that area. So for example, to estimate capital M, we have M hat is equal to lambda hat multiplied by A. And we can write that the variance of this estimate of the population size is going to be A squared multiplied by lambda hat over A times N. Okay. All right, so on Friday, we'll just go over this explanation again to start, and then we'll work through the example given on slide 10. Just a reminder that the final exam is on Friday, April 16th. It's from 9 to 12. It'll be held in the exact same way that the quizzes have been held, so please let me know if you would prefer to write online. And then the other thing I just wanted to ask, if you guys have time, could you please fill out your student evaluations? This is good for, of course, all the faculty that have been working with you throughout the semester. And your feedback is, of course, helpful for, in my particular case, for development going forward. So if you have time, I would appreciate it if you could fill out your student evals before the semester is over, or course evals before the semester is over. Right? Okay, so I'll talk to you guys on Friday. If you have any questions, please let me know. And again, we only have assignment 4 left in terms of assessment before the final exam. So have a good couple of days, and I will chat with you in a couple days.